Okay, so last time this question we solved in the class, right? So let's do the second part of that question. So in this question, if you remember, there were almost every component possible shown. Two-stage compression with intercooling, right? So here you saw two-stage compression with intercooling. Then there was regeneration. Then there was combustion chamber 1. Then high pressure turbine just to run these two compressors. And then there was the reheater, another combustion chamber or a same combustion chamber. So that was reheating, and then the low pressure turbine for power output, net power output. And the exhaust is flowing towards that heat exchanger. So this heat exchanger is actually a gas to gas heat exchanger. But on one side, from 9 to 10, these are exhaust gases flowing. But from 4 to 5, it's air, right? Pure air. So this was its TS diagram. And in this problem, the isentropic efficiencies of compressors and turbines were given, right? But in this question, the pressure drop during heat transfer processes like combustion chamber 1 and 2 and intercooler, and also this heat exchanger for regeneration purpose. In all these heat exchange devices, the pressure was assumed constant. Wherever there was a heat transfer process, pressure was assumed constant, right? But isentropic efficiencies were taken into account, and also there was a mechanical efficiency of this shaft, of this high turbine shaft, and also for this low pressure turbine shaft were also given, right? So then for this question, we calculated the cycle efficiency, which was 28.8%, and the work ratio was 0.35 or 35.8. Now the next problem is then we also calculated mass flow rate of the air flowing through that one. Now, in the next part of this question, we will see the effect of pressure losses in this system. So the pressure losses assumed, normally we neglect those pressure losses in majority of those calculations, which we have done, not only in this chapter, but also in the previous chapter. But all the real world system, whenever there is a fluid flowing through any duct or passage, so it comes in contact with the walls of that surface, so there will always be pressure losses, right? And if you remember, you can calculate those pressure losses with the help of fluid mechanics equations. If you remember that Darcy's equation, which can give us this head loss, FL V square over 2GT, right? So using this equation and using those Moody charts or equations to find out this friction factor, we can estimate that head loss also we can represent it in terms of delta P pressure loss, right? So in all real world system, there will be certain pressure losses. So because of friction and turbulence. So we will see where in this particular system, this friction and turbulence, we cannot neglect, or if those are prominent, then we have to include in our calculations. So here you can see there will be pressure loss in the intercooler. Fluid is flowing through some piping, then air side and gas side of the heat exchangers, means this one. This is air side of that heat exchanger, and this one is gas side of the heat exchanger. So it means this is referring to this part. Combustion chambers, of course, fluid is flowing through a combustion chamber. And exhaust duct, this one, right? And of course, all the ducts which are connecting those components between compressor and intercooler and compressor, and so on. So in combustion chamber, of course, the heat is supplied. The major amount of heat which is added to the system is in those combustion chambers. So because of this heat supply, temperature rises to a very large value. So there will be a high gas velocity because of the expansion of that fluid. Um, and also because in the combustion chamber, the cross-sectional area is normally not changing. So this is a constant cross-sectional area. So now because of very high heat transfer and very high temperature, velocity increases. And we know from this equation, the increase in velocity to the scared will be the pressure drop or head loss, right? So these are the reasons due to which there will be pressure drops in different components of these systems. So now we will solve that question. It is exactly the same question which we solved previously. But now in this question, every other data is same, except now there are pressure drops given. So let's see what are the pressure drops given. For example, this one, air side heat exchanger means air side is this process 4 to 5. For this air side, this delta P is given drop in pressure. So in other words, that is P5 minus, sorry, P4 minus P5 is given as 0.3 bars. Similarly, gas side heat exchanger and exhaust duct means from 9 to 10, this pressure drop is given, right? P9 minus P10 is given as 0.05 bar. Intercooler from 2 to 3. So here this pressure drop is given P2 minus P3. Similarly, for each combustion chamber means P5 minus P6, and the other one is P7 minus P8. These two pressure drops are also given as 0.2 bars. Ambient pressure is given as 1.01 bar, means P1. This value is representing P1. And also P10. So both P1 and P10 are 1.01 bar. This is also 1.0. Sorry. Okay. Pressure ratio for each compressor means for each compressor means P2 by P1. This is one compressor and this is second compressor. For both compressors, pressure ratio is same. P2 by P1 is equal to P3 by P1 is equal to 3, which was same as in the previous problem also. As previously calculated, and find a new overall. Now we have to find out new overall pressure ratio. Overall pressure ratio means P4 by P1, because in between there is an intercooler. because in between there is an intercooler and there is a pressure drop. So that's why P4 by P1 will be different. But for each stage, the pressure ratio is same as 3. Okay. And we also need to calculate the new cycle efficiency for these pressure drops and work ratio. Okay. So we shall see how much is the effect on cycle efficiency and work ratio of all these pressure drops. Right. The rest of the data, which is not mentioned here, it is same as in the previous example. Okay. So now we shall draw its TS diagram again, because now pressures are changing. So let me draw the TS diagram step by step. Okay, so let's start from state 1, which is low pressure. So let me show it like this. So now this is P1. Let me show here 0.1. Then there is P2. This one. P1 to P2, and of course isentropic points are given. So we can show it as 2S and 2A. Okay. But now P3 is not same as P2, because here in the intercooler, because now at point 2 fluid is entering in the intercooler, and in the intercooler the pressure drop is given, pressure loss is given. So it means from point 2 to point 3 there will be a pressure drop. So I should show point 3 something like this. This is P3, which is smaller than P2, right? But in the book there is this one little mistake I found out. He's showing P3 greater than P2, but actually P3 is smaller than P2, right? So be careful here. So then 0.3 is somewhere here, because from 2 to 3, actually it is 2A to 0.3, there is small pressure drop, and that is given as 0.15. Okay, so maybe I can write pressure values. P1 is equal to 1.01 bar. P2 is, because pressure ratio is given, so 3 is the pressure ratio multiplied by 1.01. So that is 3.03 bars. And 0.3 pressure will be P3 is equal to P2 minus 0.15. So here is P2, 3.03 minus 0.15. So that will be P3, which is 2.88 bars. Then 3 to 4. 3 to 4, another compression. So let me show both 4S and 4A. Okay. So P4, now P3 is given, I can find out P4. P4 will be equal to, again, this pressure ratio, P3 by P4 is also 3, or P4 by P3 is also 3. So that's why P4 will be equal to 3 multiplied by 2.88. So that is now new P4, which is 8.64 bars. Okay, so far everything is clear. Starting from 1 to 4, there is a pressure drop between 2 and 3. So both are not on the same line, right? There is a pressure drop. So now we shall continue from point 4 up to point 5. So then 4 to 5, again, there is a pressure drop in the heat exchanger. So 4 to 5 is air side of heat exchanger. So there is now a pressure drop of 0.3 bars. So P5 will not be at the same line as P4. So I have to show P5. Okay. So that will be P5, a little lower than. So somewhere here. Point 4 to 5, there is a heat transfer, but pressure is also dropped. And so this P5 will be P4 minus 0.3 bars. So this will be P5, 8.34 bars. Okay. Then from 5 to 6, there is combustion chamber. So again, there is a pressure drop from 5 to 6 for each combustion chamber. Pressure drop is given. So I will show 0.6 pressure, something like this. Okay. So for example, this is 0.6 now. Okay. So 0.6 temperature, which was given, it is the same, but now the pressure is a little lower. I think it was 650 in the previous question. So all of the data which was available in the previous example, that is valid here. Only the pressures values are now changed. So now P6 will be P5, which is this one, minus 0.2. So I will say this P6 is equal to P5 minus 0.2. So this is new P6. This is 8.14 bar. 8.14 bar. Okay. Then 6 to 7 turbine. All right. So this will be same as before. This process 7S, 7A, isentropic efficiencies of turbines and compressors were given. Then 7 to 8, 7 to 8, another combustion chamber. But now again, during this heat transfer process, pressure drops. So now the P8 will be somewhere lower than P7. But 0.8 temperature will be same as 0.6 because there is nothing mentioned about the temperature change. Only pressure changes are mentioned here in this example. So P from 7 to 8, again pressure drops. So P8 pressure will be, let me show it here. P8 will be equal to P7 minus 0.2. For each combustion chamber, the pressure drop is given as 0.2. So P8 will be 1.743 bars. Then from 8 to 9 and 9A. Hopefully it is visible. I'm right in the corner. 9.7, 9A. That is second turbine, low pressure turbine. So isentropic and non-isentropic. Now from 9 to 10, it is the gas side of the same heat exchanger, regenerative. So 9 to 10, there is a gas side heat exchanger, and this pressure drop is given as 0.05 bars. So from 9 to 10, let me show 10, something like this, because there is again a pressure drop from 9 to 10. So now where should I show 10? 10 will be higher than 4. Yes. Yeah, 10 will be a little because this heat exchanger efficiency was also given. It was not 100% effectiveness heat exchanger. So 10 maybe I should show a little higher than, okay, somewhere here, 9 to 10. And point 10 pressure will be same as 1 because 10 is going into the ambient, right? So it means P10 will be equal to P1, and that is 1.01 bar. So now I can find out P9. P9 will be this one. Let me show it here. P9 will be equal to P10 plus 0.0, how much? 0.05 bar. Because P9 is higher than 10, but 0.10 we know it is going into the ambient, so that's why it will be ambient pressure. So P9 is equal to P10 plus 0.05, so that is 1.06 bars. Okay, so that completes the TS diagram. Now, if you want, you can join these heat transfer points with dotted lines because pressure drop means there is a energy loss due to friction, and which makes the process irreversible, right? So irreversible processes normally we show with dotted lines. So whether you show or you do not show it, it's okay. We know what is happening there. So in the book is not joining these lines. Main focus is that we should be able to show the pressure lines clearly. Okay, the rest of course is clear from here, what is happening between 1 and 2, between 2 and 3, and so on. Okay, so this will be TS diagram for this question. And now once this TS diagram is drawn, now we have to find out all the unknowns, all the unknown temperatures, pressures are, we have already written it, but unknown temperatures so that we can find out efficiencies and work ratio and whatever is needed to be calculated. So any questions so far in this TS diagram? So see in the book, there is this little mistake which I found. They have shown P3 higher than P2, but actually P3 is lower than P2. Okay, so no question. So then let's continue. So I will remove it. I have made this figure separately also in the next slide. I have added here. Okay, based on these delta P's which are given. Okay, now so we shall solve this diagram. Sorry, solve this question. Let me, okay. Okay, so now we need to find out all those unknowns. Unknowns are again cycle efficiency and work ratio. So just like in steam turbine power plant, let's we calculate enthalpy. So here we will calculate all the unknown temperatures. So let's start from this process, pressure change in the first compressor, low pressure compressor. So this process is very much same as before because nothing is changed here compared to previous question, right? So you will get the same values of temperature. And I've written it as before because there is no change here because this pressure ratio is same as before. P2 by P1 is equal to 3. Okay, gamma is same, T1 is same. So we will get the same 2S as in the previous part. And then using the isentropic efficiency of compressor, low pressure compressor, which is also same. So we'll get the same T2. So in this part, there is no change. right? And the work input to this low pressure compressor is simply given by Cp into T2 minus T1. So that will also be same as before, right? This one. So there is no change in the work input of low stage compressor, right? Because this pressure ratio was same. Now we shall see for the next compressor, 3 to 4. So what you think, will there be any change here also? Yeah, P3 is changed. P3 before was different, but what about P3 by P4 or P4 by P3? Does it changed or not? This pressure ratio P4 by P3.
Pressure ratio does not change, but the value is changed.
Yeah, value is changed, but pressure ratio is still same 3, right? And that is required to calculate T4. S over T4 and then T4. Isentropic efficiency is same. So it means I will, and T3 is equal to T1, that is also same. Although pressure value is same, but still it cools down to the same initial temperature. So I would say that T4 will be, as in the previous question, T4 will be equal to T2. So I think there will be no change even here for the second stage compressor. So if there is no change in both of these compressors, so it means the work input of one compressor is this one. So the work input of the other compressor will also be the same because there is no change. T4 minus T3 will be same, right? So, but the overall pressure ratio from P1 to P4, now we have to see will it be same or not. Okay, so P2 by P1 is given as 3. So from here, I can find out P2. So P2 comes out to be 3.03 bars. Okay. And P3, we already, I think I calculated on that diagram which I draw, that P3 is 2.88 bars. Now we said that P4 over P3 is same pressure ratio, but now P4 value will be different because P3 is changed. So now from here I can find out P4. So that comes out to be 8.64 bar. So now the overall pressure ratio will be P4 by P1. So the overall pressure ratio from 1 to 4 will be different. So P4 is 8.64 and P1 is 1.01. So that comes out to be 8.555. So overall pressure ratio is now different, right? Because of the pressure drop. So that is one of the questions. Find a new overall pressure ratio. So that has changed. Okay. So that is done here. This part. This is the new overall pressure ratio. Then we calculated P5 already. Because there is a pressure drop from 0.4 to 5. I already explained on TS diagram. So then next is now we need to calculate the work output of high pressure turbine, because now work input of the compressors are known, which was for low pressure compressor, we calculated it to be 133.1. So there are two compressors, so that will be 2. And this work has to be supplied from the high pressure turbine. So high pressure turbine has to give this work but there is mechanical efficiency of this shaft is given. So within this high pressure turbine, how much work is produced? This much divided by 0.98. The remaining 2% is lost somewhere here, right? But that is the energy which will be produced within the turbine. That is work output of HPT, high pressure turbine. This is same which we already did in the previous question. That is 272 kilojoules per kilogram. Okay, now once this work of turbine is given, this one for this 6 to 7 process, we have calculated temperatures 1, 2, 3, and 4, right, already. Uh, zero point 0.5 temperature we will calculate from the heat exchanger. So that's why now I am at 0.6, 6 to 7. 6 is already given. 6 and 8 temperatures are given as 650. So now the target is to find out T7. And T7 we can calculate from this work of turbine, which is equal to work of compressor. But inside the turbine, more energy will be developed. That's why we are dividing with 0.98 because the 2% will be lost. So that comes out to be 272. So now put this 272 is equal to, that is the work output of turbine. Cp into T6 minus T7. So T6 is given. So from here we can find out T7. Actually, this part is same as in the previous example. There is no change here as such. Although pressure is changed, but this pressure is not used to calculate T7. Right? We are using the work of turbine, and work of turbine is equal to the work of compressor. So that's why this will give us T7. But now using this T7, we can calculate T7s from the isentropic efficiency of high pressure turbine, which is given. T6 is 650. Okay. T7 is calculated. So from here, we'll calculate T7s. Okay. So T7s, according to this graph, will be lower than T7. So that's how you can check whether your calculations are going correct or not. This is T7. This is higher than T7s because of the non-isentropic effects. Okay. So this is same as before, this part. There is no change because the no pressure term is involved here. Okay. Now, what will be P6 by P7? That is the question now. P6 by P7. P6 by P7, which we calculated in the previous part, that was 4.19, if you remember. And how we calculated this one? From T6 over T7s, if you remember. Because this is given, this is calculated, and using this again isentropic correlation, that will be K over K minus 1. And then we find out this P6 by P7. Actually, this will shift here. So because T6 and T7s are same as before, so that's why this ratio will again be same, right? This P6 by P7, which we are calculating from T6 by T7, and T6 and T7s comes out to be same as in the previous part. So this ratio will be same. Although individual pressures will be different now, but ratio is still the same as before. Yeah. So if this is clear, now we can find out P7, right? So P7, we now calculate from this ratio. because P6 is now new P6, which we already discussed. Okay. So put this new P6, so we'll get new P7. Okay. Because when I draw that TS diagram, I did not write the value of P7 there because this was not known at that time. So now we know this is P7 because P6 is changed, but P6 by P7 is same. Okay. Then P8 is again P8 will be P7 minus this pressure drop in the second combustion chamber. So that will be P7 minus 0.2. That will be P8 because this pressure drop in the second combustion chamber is given. So that is 1.743. So that will be P8. Okay. So that is done next. That is P8, new P8. Next, P10 is equal to P1, we already know. And from there, we calculated P9, which I already explained this part when we were drawing this TS diagram. Okay. So now let's see this part. T8 temperature is same as T6, 650. Because there is nothing mentioned that in this temperature has changed. So if nothing is mentioned, so we'll take it as before. So this T6 is equal to T8. During reheating, it achieves the same temperature. But now we need to find out T9, right? So for T9, next is P8 over P9. P9S is equal to T8 over P9S to the power K minus 1 over K. Because this is an isentropic expansion process. So now from here, we can find out P8 is now known separately, 1.743 bars, and P9 is already, we discussed that will be 1.06 bar. Okay, so from here we can find out T9 is T8 is 650 plus 273. Always remember single T, that must be Kelvin. So this will give us T9S. So T9S will be, I have it here, 815.4 Kelvin. Then use the isentropic efficiency of turbine formula. Actual divided by isentropic, T9S. So that will give us T9. And T9 must be higher than 9S. So T9 will be 831. I have it here, 831.5 Kelvin. So T9 is higher than 9S. Okay. So now this temperature is also known. So all the temperatures which are required to calculate efficiency are now known, except this T5, which was left, because now we can find out T5 also. So here is that procedure for calculation of 9S and 9 temperature. Now, the temperature which is left is the T5. So do we really need T5 anywhere? Okay, anyways, let's write the heat exchanger effectiveness formula. That is T T5 minus T4 actual heat transfer divided by maximum possible will be T9 minus T4, maximum possible temperature difference. Okay. Uh, if you forgot this thing, see the lectures of heat exchanger from heat transfer, where we discussed this thing with respect to counterflow heat exchanger. So actual Cp will cancel with Cp. We are taking constant Cp so far, divided by maximum possible. And that effectiveness or thermal ratio is the term which is used here. That was given as how much? 0 point something. I don't know, 0.75 was. So this will give us T5. All right, so once you know T5, now you can find out T10 also. If you say this enthalpy change, T4 minus T5 is equal to T9 minus T10. If you are interested, you can find out T10 from here. This enthalpy change or heat lost by this fluid is equal to heat gained by this fluid is equal to heat lost by this fluid. So that can give us T10. But T10 is not required anywhere to calculate efficiency or any other thing. So now we can find out network output. Network output of this system is this one, 8 to 9 process. Okay, because the work output of this turbine is only used to run these compressors. So this is our network output only here. So we know all those temperatures. So just put the values. So that is the network output. And I already explained how to find out T5 because I need this T5 to calculate heat transfer because now I also need Qin. So the heat is transferred from 5 to 6, from 5 to 6 process. That is Qin1, and from 7 to 8, that is Qin2. Okay. So it means Qin1 is Cp, but be careful, it is gas. So Cpg into T6 minus T5 plus Cp, still gas, not air, that's not pure air, into T8 minus T7. So all these temperatures we already have. Just put this will be total Qin. Okay, so that is done in the next slide. So here is the heat supplied. So now finally we can find out the efficiency. W net out divided by total Qin. Just put the values. So here is the cycle efficiency. W net divided by Qin. That is capital W, I think. No, actually it's small w. We are calculating everything for kilojoules per kilogram. So that is correct. Here it should be small Qin because mass flow rate is taken as 1. So here you can see the cycle efficiency is 21.2, and in the previous problem where the pressure drops were not taken into account, all those heat transfer processes were taking place at constant pressure. So the efficiency was 28.8%. So here you can see the effect of those frictional losses during heat transfer process is this much. Okay, because this is all due to friction. So that is a significant drop in efficiency, almost 7 to 8%. Okay. Only when we have taken into account those small pressure drops, although those were small, but still they're their effect is significant on the final efficiency. Now the gross work output, now we need to find out the work ratio. So work ratio is equal to net work output divided by work of high pressure turbine plus work of low pressure turbine. That is how we define work ratio. Okay, net work output already calculated this one. Net work output and work of high pressure turbine plus work of low pressure turbine. This is also calculated from compressor, and this is also the same thing. This will give us work ratio 0.274, and the work ratio before, when we neglected pressure losses in the previous question, was 0.35. So here again you see a drop in this value by 8% almost. Okay. So in actual calculation, so it means this effect of pressure drop should not be neglected, by the way. So here, because in our basic courses in thermodynamics, we normally neglect this effect, but here we have seen, because uh, these pressure drops were given here. Actually, those pressure drops you have to calculate separately using that formula, which you learned in, or the procedure which you studied in fluid mechanics. So that is a separate task, separate computations which you have to perform to find out those pressure drops. So here those typical pressure drops were given, right? Okay, so but still you see here the effect of pressure drop on efficiency, which we normally neglect, is actually not negligible. That is also quite significant. That's why in these practice problems, you will see many problems where pressure drops are actually given. Okay, so what's the time now? Okay, okay, there will be one more question I have added. It's looks much simpler just by looking at it, because it's just single compressor, single turbine, and just one regeneration processes. But here again, the pressure drops are given. Okay, isentropic efficiencies are given. So you will see that that makes this problem quite complex too. I think that is problem 9.8. All right. So I will solve it in the tutorial class today. Okay. So that will be the last question which I will solve from this chapter. So the solutions which I have shared with you from this book of McConkie, be careful. There will be there are some mistakes, not in the solution, but maybe in this TS diagram. So I have corrected the TS diagram of this problem 9.8, I think, because in those solutions, very old solutions, this TS diagram doesn't look good. So I corrected it here. So be careful about the TS diagrams. Okay. Okay, I stop here. Any questions? So we shall do this problem in the tutorial class.